This BBC podcast is supported by ads outside the UK.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
You're about to listen to a brand new episode of Curious Cases. Shows are going to be released weekly, wherever you get your podcasts. But if you're in the UK, you can listen to the latest episodes first on BBC Sounds. I'm Hannah Fry.
And I'm Dara O'Brien.
And this is Curious Cases.
The show where we take your quirkiest questions,
your crunchiest conundrums,
and then we solve them.
With the power of science.
I mean, do we always solve them?
I mean, the hit rate's pretty low.
But it is with science.
It is with science.
Do you know the way there's things you think, why haven't they invented this?
Right.
Yeah. And I'm hoping that if we say them, then people will go and invent them. But do you know the greatest invention I ever heard of?
Tell me.
It's called the back home button.
Right.
Yeah.
Have you got any of the technical...
The technical details are somebody else's problem. And it's raised more as a kind of a philosophical, what would you give if you, at the end of an evening, could just press a button and then be instantly transported, not just to your home, but properly underneath the duvet, all cuddled up. And then you go there, go and find the home. It's grand. You know, you stumble out of the club, you know.
You do.
Yeah, I do. And then beats are still pounding in your head. But you got to navigate your way back, and buses and taxis or whatever you're doing.
I think it's when you've been on a work trip and you're in some airport getting budget airline home. What I would give for a back home button right then.
Yeah, I think it is a
all
thing.
my worldly possessions, apart from my actual home and the duvet.
Yeah. Just leave me the bed.
Press the button and get home, and you don't have a home anymore. That would do.
And I know technically that's teleportation. That's what it will require.
Yeah. We have got a question that aligns with this topic because Faith has written into Curious Cases at bbc.co.uk, and here's what she had to say.
Hello, Curious Cases. My name is Faith, I'm 13, and I would like to know if a Star Trek transporter would ever actually work. Is it possible to physically deconstruct someone and put them together in a different place, like in Star Trek? Or is this completely science fiction?
Faith, thank you, Faith, has made this question sound more scientific than I made.
Well, you know what? If we're going to go down the science road, because this is a science podcast, I think there's only one bit of science which we should turn to, and that, of course, is the quantum world. And luckily for you, Faith and Dara combined, we have got not one but two amazing quantum experts joining us.
Yes, quantum computing expert, Professor Winfried Hensinger. What an excellent name for a quantum physicist.
Absolutely. It sort of can be anything until you observe it.
Oh, right? You observe and you go, that feels like a 1930s quantum physicist. Professor Winfried Hensinger from the University of Sussex, he is, and Professor Yvette Fuentes, quantum physicist at the University of Southampton. Thank you both for joining us. Are you both, by the way, science fiction fans?
Yes.
100%. That's how it started for me, actually.
Oh, same for me.
Oh, really?
Yeah.
Oh, that's great. It feels like that's our best example of teleportation.
So Faith asked about teleportation. So did I. In primary school, asked my mom, what do I need to study to build a teleportation device? And so I decided in primary school that I would study physics based on the very question your listener has just asked.
Well, Faith is 13, so I'm afraid she's late by about... She's missed the boat by 2 years. I'm joking, Faith, I'm joking.
It's a perfect time to ask this question, Dia, Scott, and yourself as well.
I also felt very connected to the situation because when I was maybe 9 or 10, Star Wars came up, and I've never seen a film like that. And I went to the cinema, and I came out jumping, thinking oh my God, I want to be on a spaceship. I can understand her passion.
Delighted to put this in that context of fangirling, fanboying over this as an idea, because you both work in quantum mechanics. Okay,
yes.
Mm-hmm. Can either of you, and this is I know a ridiculous question to ask, sum up quantum mechanics for us in a couple of sentences?
Well, quantum mechanics is the physics that describes very small particles like electrons and atoms, but it's very different to the physics that we know, that we call classical physics, Newton's laws.
Also, a branch of physics which tends to be counterintuitive, surprising, would you say?
100%. I mean, I would take this one step further and say this is the very foundational theory describing everything. And it is super counterintuitive. There's lots of really counterintuitive things in this theory, such as that two objects can somehow be connected, even from they're on the other end of the universe. Or one object can be at two different places at the same time. That's the idea of superposition.
So hang on, is quantum physics the right bit of science that we need for teleportation? And before you answer, please say yes, because we've got no other guests.
Definitely, yes.
Absolutely.
Okay, good.
So why? What is it that you can use for this ridiculously almost impossible task?
Okay, because quantum teleportation uses entanglement, and entanglement is a property of quantum systems.
Okay, what is that property?
Okay, so let me explain what entanglement is using an example that was used by John Bell. So John Bell wrote a very important theorem about quantum mechanics, and he had a student called Bertelmann. He always wore one sock green on one foot and a red one on the other. So if you wanted to see what socks he was wearing, you would see a green one on his right shoe. You immediately knew that on the other leg he had the other color. John Bell used Bertelmann's socks to explain what classical correlations are. Actually, I know Bertelmann, and he's 80 years old now. He still has one red and one green.
But wait, did you only ask him to show you one leg so you could infer what the other sock was when you met him?
Yes.
Okay, great.
Guess. So I thought that maybe we could talk about entanglement if Hannah wants to play Bertelmann's socks.
Sure.
With me. We have a bunch of socks, red and green, and we talk in the morning, and you tell me, like, I'm going to wear red, and then I wear green, okay? And let's say we come every day here to work, and every time we show our socks, it gets a little boring, right? Because Monday you have red and I have green, but then Tuesday, because we agreed, I'll have green and you'll have red, and every single day we have this, we call it correlation, because they're somehow connected. But this is all classical. Now imagine that we have these sort of, I don't want to call them magical, but well, why not? Let's call them some special socks. They're quantum socks. The socks are red and green in a superposition at the same time. So you don't even know which one are they. When I look at them, half of the time they will be red and half of the time they will be green. So because our quantum socks were made by the same person, mine are the same. So when we come to work, they will ask you to show your socks, and then yours will be, let's say, red, and mine will immediately be green. So you ask, how is this different from the classical game that we were playing, right? Well, it's different that your socks are red and green at the same time until they're measured. But in the moment that the rest of the team sees them, mine change color immediately.
So there's like the sort of uncertainty in what colour they are until someone looks at them, at which point all of that uncertainty collapses in both my socks and yours.
Exactly.
Right.
Yes. So that's very different, right, to what we're used to. We don't see that happening with normal socks.
Just going to say that I don't wear socks. I wear a box with a cat in it, and I walk around all day with the box and the cat in it. And I don't know how the cats do.
How is it doing?
We don't know. I've got to check.
Live
we don't know. I must check. I mean, sometimes you can feel it moving around, but sometimes you can't. But it could still be there. I'm sorry. Am I confusing our quantum metaphors here slightly?
Is the cat called Schrödinger?
Yeah.
But wasn't the whole point of Schrödinger's cat not that it was like, hey guys, look, here's a way to explain it? Wasn't it a way to sort of ridicule the absurdity of quantum? Like, guys, if you think of the implications of this, then this is the sort of situation that you would have. The ridiculous scenario where a cat is both alive and dead, and obviously that can't be true.
Schrödinger
sort of like
was very worried.
Right.
He was very worried. He really didn't like it. And he used that example to see, look, if particles can be in a superposition of two different situations, quantum mechanics makes no sense. It's absurd. How could we have a cat being dead and alive at the same time?
But it failed as a piece of ridicule because It is that.
Yeah, but also, guys, this is absurd. Are you sure? Are you sure this is what's going on? It doesn't make any sense.
So we do experiments every day. And my PhD students in the lab every day see all of that happening. Not with cats, but with atoms.
Because presumably the point of the Bertelsmann's socks is that Bertelsmann can walk away to the other side of the planet, can walk away to Alpha Centauri, can walk away to the surface of a distant moon. And the minute you check the socks near you, his socks immediately pick a side.
The distance doesn't matter, and also they don't have to talk like in the classical situation. No, I explained that like Hannah and I would have to talk on the phone and agree if you wear red. But with the quantum, you don't need to agree in that way.
Tell me what brings us back to teleportation.
So, first of all, let me tell you what we teleport, because if you're a fan of Star Trek, you might think that what you're teleporting are the atoms, no? So the typical teleportation protocol in Star Trek is that you go into a machine and then suddenly you disappear and you appear somewhere else. So that looks like your atoms actually went from one place to another. But actually, we don't teleport matter. What we teleport is just the information of the matter. So let's say, for example, that I have a particle and it has a property that is pointing up or down. So classically it would be either up or down, but quantum mechanically is in the superposition of up and down. So what we teleport is that information in the superposition. In what combination of up and down it is.
And at the end of whatever you make you observe, you measure, you test, the very first one makes the second one, the far away one, switch to being essentially a copy.
Yes.
Because its properties are the same as the first one.
Yes.
Okay, so now you have, it's not teleportation, I suppose. We'll keep moving away from teleportation, we know from the movies, but now you've got two identical copies of this electron.
Yes.
But you're teleporting information there rather than actual things, aren't you?
Yes. Mm-hmm.
I mean, like, going back to your socks thing, which I loved. I'm sort of imagining this digital pair of socks which is like swirling different colours until it gets settled. Okay, sure, like, you can settle my pair of socks and immediately yours settle, and there's information that's teleported. But can you teleport actual objects?
No.
Even like subatomic objects?
No, that's I'm sorry to be like the fun killer. I would love that, but we can't do that. So let's say again with the game with the socks, we cannot teleport like my socks into your house. What we teleport is just the information about what is the state of the sock. Is the sock red or green or in a superposition, but not the sock itself.
But I mean, maybe it's helpful to think about what we are. So essentially, we are just made out of atoms, right? So you're essentially pretty much mostly water and a bunch of other stuff, right?
How dare you?
So, so at the end of the day, like, what makes us distinct from just a bunch of water and a bunch of other stuff? That's the first question you have to ask. And what makes us distinct is actually the quantum state.
Right.
So the state of the atoms is what makes it important. And the good news is that we can teleport the state of one atom at a time. That works. And now people have already started actually to do something really crazy, and that is to entangle or create superposition of macroscopic objects too.
So what's the largest object that has been teleported?
There's been able to teleport a group of atoms, and let's say like 10 to the 13 atoms.
That's loads.
That is a lot.
How many are there in a human?
You know what? That is like the size of a small particle, like a dust particle. That's what we've been able to teleport. And remember the information of it, right? But not from one star to another, but from, a small place in the lab to another. That is like a meter, let's say, maximum.
Okay, I mean, look, it's a start.
It's a start. I mean, that's a lot. That's a lot. That's 10 to the 13 atoms.
How many are there in a human?
10 to the 27. Right. Which is not, by the way, twice as many. That is
many times 10 more. Also, presumably a lot more screaming would be involved.
I mean, look at the ouch part of all this. But on the other side, what are you building the replica out of?
So you would have to have a copy of all, let's say, if we're made of carbon, oxygen, nitrogen, you would have to have the same sort of ingredients, let's say, on the other side.
And that's kind of how our Spock beams down, like on the Enterprise, right? Having a bunch of atoms on the Enterprise and a bunch of atoms on the planet. And what we need to do is we need to read out this quantum state of the atoms on the Enterprise. And then essentially there is what's called, unfortunately, a no-cloning theory. So we can't clone a person by teleporting them. Now, the only way I can determine the quantum state of that being on the Enterprise is actually we have to measure that. We have to open the box, right? Mm-hmm. And when we open the box, we have to, unfortunately, destroy the quantum state. And so, bang, Scotty isn't anymore on the Enterprise. He's gone because we measured his quantum state of the atoms that made up Scotty. And so now we need to take atoms on the planet. We need to inscribe the quantum state into these atoms to then recreate Scotty.
You have to have the stuff there. You can't say teleport gold to give yourself a second pile of gold, if you know what I mean.
That would be really nice, but unfortunately we can't do that.
Would you tell us if you developed that technology?
I'm not very sure I would.
Do you think we're ever going to get to human then? Do you think we'll ever get to human size?
I think it's hard. Never say never, because some of our really clever listeners who are listening right now, including a listener who asked the question, may just decide, I'm just going to invent that, I'm going to do that. Things that people thought are completely impossible to achieve, we are doing nowadays. On the other hand, I should also say that with the understanding we have right now and the technologies we use right now, it would be very, very difficult or impossible.
We don't know how to do it right now.
I mean, but look, all I heard was never say never. So that's a whole big dose of optimism. That's what I want to.
No, and the other thing is that we don't know like how gravity and quantum mechanics fall together. So our theory is incomplete.
Details.
And maybe
details.
Maybe later we can.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
Okay, here's the question though, right? Let's say that we managed to do this. I'm feeling better about it than I was earlier. Would we want to do it? What does it mean to teleport an actual human? Well, joining us, we have philosopher of science, Professor Helen Beebe from the University of Leeds with us in the studio. Are there alarms going off for you about this idea? I mean, talk to us.
Well, not so much alarms, but I think there's a really puzzling question about, so as Winfried said, when you beam Captain Kirk from the USS Enterprise to the planet, you're not transporting any matter. You're just, in some sense, reproducing Captain Kirk on the planet. And unfortunately, the original becomes deceased at that point. But there are two ways we could think about this, right? One is you've killed Captain Kirk and made a completely new person who isn't Captain Kirk at all. It's literally a different object. Or you could think that somehow what's important to the identity of Captain Kirk is not the stuff he's made of, but the information, in which case he's kind of moved from the ship to the planet. And it's just, at least when it comes to people, I think most of us are just kind of a bit conflicted. We're not sure what to say. So like if you think about a sort of a non-sciencey case, right? So I leave my coffee cup on the table in the living room, and Hannah comes along and accidentally, smashes it to bits with a hammer.
Hey, that's the kind of thing I do.
And then thinks, Hannah might be a bit annoyed about that. Maybe I know what that mug looked like. I'm going to whip out my potter's wheel and make an exact duplicate of it. So you make an exact duplicate of it. You stick it in the kitchen cupboard. And then I get home and I find the coffee cup and I think, oh, that's weird. I could have sworn I left that on the living room table. It must have moved. Now, I'd be wrong, right? The coffee cup has not moved from the table to the cupboard. The original coffee cup has gone and a new cup is in the cupboard. That's just the way we think about coffee cups, right? There's no sense in which the cup has moved from the table to the cupboard. I'm just mistaken about that. But if you think about something like, text messages, right? So I've got my phone set up so that when I send you a text message, at the moment it arrives with you, it disappears from my phone. we think of them differently, right? It's like I sent you a text message. It sort of, in some sense, moved from my phone over here to your phone over there. We do think of that as, well, that's the same text message. So now there's a question, kind of like, are people more like text messages, or are they more like coffee cups? Because in a sense, what we've done to Captain Kirk is exactly what we did with the coffee cup, right? You destroy the original, you make a new one. Do we think it's a new person who isn't Captain Kirk at all? He just mistakenly thinks he is. Because, of course, from his point of view, it's like, oh, 1 minute I'm on the ship. Oh, next minute I'm on the planet. Marvellous. But from the original Captain Kirk's point of view, it might be a bit like, oh, you're going to kill me. But I'm not sure I'm happy about that.
But then I also wonder, though, okay, the difference between the coffee cup and the text messages, that the text messages is about information travelling rather than necessarily physical atoms. And I sort of wonder about, in the Captain Kirk example, for me, there's a lot about, like, if it is the same person, they should retain the same memories.
Yeah, I think that's kind of the question, right? What is it that's important for our own identity as people? Is it the stuff we're made of, so that if you do the transporter beam with Captain Kirk, it's like the coffee cup? Or is it the memories, the aspirations, the character, all of which I take it would be preserved? And it doesn't really matter that I've just reassembled you out of a bunch of stuff lying around on the planet. It's still going to be you.
Is it the physical stuff, or is it the information that makes us human? It feels like we have got very deep here. So what do you think of it? Is it the same Captain Kirk? Is he going to remember where he left his car keys? Oh.
I'm not very sure. I think we don't know yet if everything we are just a bunch of atoms and, let's say, fields and information. I think this is one of the big philosophical questions that people take different perspectives. Maybe people that are religious as well would have a different point of view, which is also valid, to say, are we just a bunch of atoms? Are we just made of matter, or is there something else? I mean, something interesting also to think about is that when we were children, of course, we were also made out of atoms, but those atoms are not the same atoms now. So what makes us?
The mind-blowing question as a kid was, would they say your cells regenerate after X number of weeks or months? So it's not, I mean, it's a bit Ship of Theseus, Sugar Babes paradox of...
Trigger's brush, thank you very much.
We all have our own favourite one of those. Sugar Babes is the proper philosophical. But it is but the notion that we aren't really the same thing anyway. I think it's, just to earth this philosophical discussion, could we just try to learn to teleport a coffee cup first before we start worrying about how we teleport our own consciousness? Like, that surely there is a distinction there between what we could or could not teleport, depending on our consciousness, on it having a consciousness.
All I'm saying here is the price that you pay for the back home button suddenly went up. It's like, yes, the price you're paying is not being sure whether you really are yourself anymore.
I mean, outside the nightclub, as people just collapse into a heap dead, and their actual copy then are fine sitting at home.
Oh yeah, would you transport your hangover? That's
oh, that's a very good point, actually. Yeah, if you excise that,
the quantum state of a hangover.
The thing is, would you volunteer to be teleported?
I'm all right, thanks.
I think we all, after watching The Fly, or what was that film? Like, I think we all kind of.
I'll just take the budget airline flight home. Thanks very much.
Yeah. It does feel that you need one person somewhere else. You need a pile of skin and bone cells sitting somewhere else, and you need some sort of extra, and then you need a 3D printer that basically gets all the squelchy stuff and goes bzzz, and prints up the person while the person is going, so what do I do now? Oh, you just die. You just die, that's what you do. We can agree that you can use it for quantum computing. Okay, in what way do you use it, and what does it do?
So should I start by even explaining what a quantum computer is?
Probably
most people don't.
How does it differ from what we have?
So a normal computer processes information in bits. So essentially, like I put some number in that is a string of zeros and ones, and that's being computed inside a processor, and out comes the answer. So for example, if I want to multiply two numbers, I put them in as two true strings of zeros and ones, and it's being using logical gates inside a processor.
Yeah, it's basically a switch that's either one or zero. Yeah.
Exactly. And so in a quantum computer, that's a little bit different, because now suddenly we have quantum bits. So a quantum bit is not 0 or 1. A quantum bit can be 0 and 1 at the same time. And now we're going to make use of superposition to encode a lot of information in a relatively small memory. And the quantum processor now does all these calculations simultaneously. And so you can see how the fact that you have a quantum bit enables a whole different way to do computation by doing all these calculations simultaneously. And so that allows us, for example, in a quantum computer to solve problems that would even take the fastest supercomputer in the world millions or billions of years to solve. A quantum computer could possibly solve that in an hour. And so what we're talking about is creating new pharmaceuticals, understanding processes in nature much better, breaking encryptions.
The example that I heard and really liked was if you imagine a maze, like the kind of ones that kids do, right, when they're drawing. If you have a classical computer doing it, it's like, okay, here we go. Right, let's check this one and then we'll go this direction, No, it didn't work. Okay, let's go back to the beginning, check this one. It has to check every single route once, one at a time. Whereas a quantum computer is more like taking a big bucket of water and like chucking it in at the top and allowing the water to drip through, testing every single possible route simultaneously. So it means that the combinations that you have to run through just disappear.
Exactly. That's exactly right. And that's exactly right. You only get one answer at the end, but it's the right answer. It's essentially the shortest way to make it to the labyrinth.
But why, and why teleportation? How teleportation?
So imagine like you have this quantum processor. Imagine you have hundreds or thousands of millions of atoms or qubits, each one of them carrying a particular function. Sometimes you might want to just quickly get the answer from that part of a quantum computer over to the other side of the quantum computer, and actually can do this immensely fast doing teleportation. And while teleportation is really hard when teleporting a person, it's actually very straightforward and very easy to do with individual atoms. And so it's immensely effective to move information very fast across your quantum computer and share that information in such a way to drastically speed up the operation of a quantum computer and make it really fast.
Yvette, we do have quantum teleportation. We use quantum teleportation.
Yes. Another place where we use teleportation is in satellite-based quantum communications. People can do quantum teleportation to send messages from one part of the planet to another, to teleport across thousands of kilometers. So we were talking at the beginning how we thought about quantum mechanics applies to the very small, but our experiments are now showing us that this is no longer true. And one of the things we don't know is, where does this stop? Can we go even to longer and longer distances? Or can we have more and more massive systems still in the quantum states? So we don't really know when quantum mechanics starts and when it ends.
So here's what I'm hearing.
Yeah.
Distance, no problem. Size, kind of a problem. We're getting there. Theoretically, absolutely possible to teleport a human. Practically, impossible. Philosophically, extremely questionable.
That is
I think the summary of where we're at.
Helen, you're not raising any objections to photons, I see, and electrons going. I mean, that philosophically we're okay with that, are we?
I do want to know what happens when you teleport Captain Kirk, when you get to the point when the physicists have worked out how to do that. And you destroy Captain Kirk because you've destroyed the quantum. Is it going to hurt? Does that hurt? What happens?
That's a very good question, because now we're getting to the engineering detail of doing this. Now let us start.
And that, I think, is episode 2.
Yeah, I feel it is. I mean, I think basically we keep the bits of Captain Kirk for when you need to transport him back again. And
just keep him as a pile of atoms in the corner.
Yeah, exactly. Yeah. He's got most of the same bits. I mean, oh my God, that went in all sorts of directions.
But the answer, Faith, is, sort of, yes. Just
seems to be.
No one's going to volunteer to try it.
But also no. I think so. Well, thank you to all of our guests, Winfried Hensinger, Yvette Fuentes and Helen Baby. Thank you very, very much.
You pressing the button?
Yeah, but all I'm doing is sending me coffee cup home. That's the,
You're just texting saying, yeah, I'm going to be 3 hours on the plane.
Yeah, so I'm going to send me mug back, because apparently I can do that, but I can't send me back. So you can send your luggage back.
That's true.
That'd be handy, and then it might be easier for us to trip home.
That would be. Or you could send the bed to you.
Okay, we worked that out. That's good. The bed goes to you, and you just sleep outside the club.
Solved. Who needs quantum physics?
You're right. If you want to be notified as soon as a new episode is released, make sure you're subscribed to Curious Cases on BBC Sounds and have push notifications turned on.
Hello, I'm Greg Jenner. I'm the host of You're Dead to Me. We are the comedy show that takes history seriously, and then we laugh at it. And in our latest series, we've covered lots of global history. We've done the American War of Independence, we've done Empress Matilda and the medieval anarchy, we've done Alexandre Dumas, the French writer, the Kellogg brothers and their health farm. We looked at the lives of Viking women, Renaissance-era beauty tips. We jumped to 18th century India and also to ancient Alexandria. We looked at the life of Hannibal of Carthage, who fought the Romans, and we've done Marie Antoinette and a big birthday special for Jane Austen. Plus, there's 140 episodes in our back catalogue, so if you want to laugh while you learn, the show's called You're Dead to Me, and you can find us first on BBC Sounds.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
This BBC podcast is supported by ads outside the UK.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
BBC Sounds. Music, radio, podcasts.
You're about to listen to a brand new episode of Curious Cases. Shows are going to be released weekly, wherever you get your podcasts. But if you're in the UK, you can listen to the latest episodes first on BBC Sounds. I'm Hannah Fry.
And I'm Dara O'Brien.
And this is Curious Cases.
The show where we take your quirkiest questions,
your crunchiest conundrums,
and then we solve them.
With the power of science.
I mean, do we always solve them?
I mean, the hit rate's pretty low.
But it is with science.
It is with science.
We have some serious news here in Curious Cases. Okay. Back in our first series, your 27th.
Sure.
Yeah. We did an episode called Mirror Mirror where we investigated the shiniest things in the world.
I remember it well.
Yeah, it's good. Really, really fun episode. And we briefly mentioned diamonds.
Yeah.
And I expressed the opinion, which I've said many times, that there is few things in life as beautiful as loose diamonds.
You love a bag of loose diamonds.
I love a bag of loose diamonds.
As you know, any good bank robber.
Yeah.
It's
not for their utility. I think they just catch the light. And you were not in favour of it.
No. I mean, look, in terms of portable wealth, I'll admit that they pack a lot of density.
Yeah.
You know, you get a lot of money per gram. I'll accept that. But I think they're nonsense. I think they are way overpriced, and I just think there's other things that are better.
Okay, that was exactly what you said. So you're consistent in this, actually.
I'm not faking this, by the way. I to my core think that they're nonsense.
Wow. Okay, but one listener was so upset that he got in touch.
Come at me if you want. I am an immovable object on this.
Oh, dear. Well, I'm going at you with the hardest substance in the world, you know, so eventually I will break you down. That's it. Yeah. You brought this on yourself.
I mean, maybe I did, but like tiny violins, you know what I mean? As we're playing in that sad music, banging jack.
It's just, I mean, we very much have guided the mood there. He's like, Guy seems actually perfectly fine about it, but
mostly I was happy that he said 20 or 30 of his colleagues were listening to your Curious Cases.
Yes, that's nice. That's
apparently we're a very big deal in Diamond.
Big shout out to the Diamond community. But I am bringing all the evidence in on this episode that will, it's going to turn you around in this. It's absolutely going to turn you around.
We'll see.
So let's start the journey to the wonder that is diamonds with the application most people associate with them, which is jewellery, of course.
Sure. It's also the one that I abhor the most.
Okay, fine, great. Let's go straight in on that day. Are they the supreme jewel? You would say no. Joining us for the first part of the show, we have Charlie Bexfield. Charlie deals in diamonds and also teaches at the Gemological Association of Great Britain. Charlie, what have you brought in for us?
So I've got 3 stones for you each.
Okay.
And 3 each, yeah, how exciting.
He's got them lying around like
you know. 3 for you.
Thank you.
And 3 for you.
Thank you.
So we have 1 is a diamond, a natural diamond. One is a synthetic moissanite.
Right.
And one is a cubic zirconia. So these are 2 diamond simulants.
So having a look at these then, so just like from the naked eye, as it were,
Yeah.
I mean, one of them is bigger than the others.
Yes.
I reckon that's a big clue that it's the cheap one. But that aside, when you do a direct comparison, it's maybe like as you look through it, it's maybe like a little greyer. How much are we talking, by the way? The diamond, the one that's the real diamond.
Yeah.
If I was buying a ring.
With that stone in it. Probably about 100 grand.
Oh.
And the other 2 are like 50 quid.
I reckon I know which one's which.
I love this.
Right, I reckon the big one, which is like much duller, much less fancy pants.
Yeah.
You know, you get it in kids' jewellery.
Right.
Right? No.
Okay.
Okay, right, this one, I reckon this is the kind of thing that you buy yourself for your 21st birthday.
Yeah.
And you feel
And if
pretty
it-
proud.
Yeah.
Very good. Yeah.
Yeah,
and if it
that's-
falls off, nobody cares too much.
No, exactly. Right, so I reckon that's that one. One thing I do know about
Moissanite.
is not how to pronounce it.
Yeah. Is it moissanite?
Moissanite. Synthetic moissanite. Yeah.
Yeah.
It's a silicon carbide.
One thing that I do know about moissanite is that isn't it sparklier than diamonds?
It has better dispersion. So it splits light better into the spectral colours, which is one of the things that we prize diamond for.
All right, but what I'm hearing here though is that one of the ways that you prize diamonds is the kind of colours that you get off it,
Yes.
and this one is more diamondy than diamonds. That's what
Well, it's
I'm
more
hearing.
dispersive, yes.
Okay, so I know which one I prefer.
Okay.
This one I think is the real diamond,
Okay.
and I think it's the real diamond just because I think just it's a bit more reflective, it's a bit more translucent.
Okay, yes.
And this one is, I think that the colour is a bit more prominent in that one there.
Okay.
That's my guess.
And if we went in terms of hardness, for example.
So we use a scale called the Mohs scale of hardness. 1 to 10, nice and simple. Diamonds at the top, 10. Talcs at the bottom, 1. And then...
What's at the bottom?
Talc.
Oh,
like talcum powder.
no, you're joking.
Yeah, talc is the best.
Yeah. Anyway, so Mr. Mohs decided to find 10 common minerals
Right.
that supposedly you could find anywhere was the idea. The aim of the game is which one scratches what.
You do like a little round robin.
Yeah, basically. You start from the softest, hopefully, and work to the hardest.
Okay, but what about moissanite though?
Moissanite's 9.25.
Right, take that. Do you know what I mean?
Yeah.
My cheap 50 quid ring.
Which sparkles more
Do you know-
and is as hard.
I don't think moissanite's a bad stone if you want something that is exactly that cheap and you don't have to
dare you.
worry about it. No, but you don't feel concerned, do you? You know, you can wear it, you can be on the tube, you can go on holiday, you can swim in the sea. Worst case scenario, it falls off and it's easily replaceable. So which one do you think's which then?
I'm going for that one for the moissanite.
Yes. Okay.
I'm going for that for the actual diamond.
Okay.
And I'm going for this as the zirconia.
This is what I think is the diamond.
So you've both chosen the moissanite as your diamond.
Wow.
Yeah.
Okay, and this big beast of a thing.
So the big one is the diamond.
No.
Yes.
Can I have it back, please?
Of course you may, yeah. That's 1 out of 3. That's almost a win.
Wow, that's really
And I got
not a
all
win
3
at all.
wrong.
Yeah.
Can I say that in my defence, the reason I didn't go for the big one
Yes.
is because it was the big
Because it's
one.
the big one, yeah.
And also because it was so sparkly that I thought all this talk about moissanite being sparkly
Yes.
influenced me into thinking, oh, this is too sparkly.
Mm-hmm.
A diamond is less showy than this. A diamond reveals its secrets in a much more demure way than this tramp of a thing that I have in my hand. Like that's basically putting on a show for nothing. But see, this has gone from being a programme about crystals into a psychology examination of what we tell ourselves are the important
But
things.
this is what I mean, right? You probably should be able to tell. You
yeah,
know?
I know.
Why?
Because otherwise the only thing that gives it value is that you know that it's expensive.
Well, no, hardly, because it's exceptionally rare. Only 1 in a million diamonds is over a carat in size. Whereas CZ moissanite, it is churned out of a factory by the kilo, by the ton.
So we shouldn't go into the diamond trade. I think if there's any summation to make from this, that we couldn't really tell at all what the difference is between them.
They are beautiful.
Yeah, you accept that at least, yes.
All three of them are beautiful.
Yeah, okay, fair enough.
Thank you so much for coming in.
A delight.
And there's 2 back, okay?
Beautiful, thank you very much.
I think we'd say we're both quite giddy after that.
You know what? I'll admit, it did have a frisson of excitement, Alan. I'll give you that.
But our aggrieved listener guy really wanted to explore the many other applications of diamond. And to help us with that, we have Mark Newton, Professor of Physics from the University of Warwick.
And we also have Julie McPherson, who is also a professor at Warwick. Right, now, Julie, this is more my language that we're talking.
Okay.
I know you're an electrochemist.
Yes.
Tell me what that is and how does it relate to diamonds?
Okay, so electrochemists like to use electricity. They use electricity to convert reactants to products. And that could be used in a fuel cell, for example. So people are thinking about electrochemistry there, or we could be making really useful chemicals. So why am I, as an electrochemist, interested in diamond? Because even at school, most people will be taught that diamond is an excellent insulator and electricity cannot pass through this structure. So what we have is a carbon atom, and it's bonded to 4 others in a tetrahedral structure. So you can actually, I've got this picture in front of me, or this prop, and actually you can see all this big tetrahedral network, and you can press against it. Actually, it's very, very strong.
Have a look.
Yeah. So that's where one of the...
That's a lattice model.
That's a lattice model, yeah. So
the tetrahedron is like a triangle-based pyramid, right?
Yeah, kind of, yeah.
And that's particularly strong just because it's
bonds,
very rigid.
Yes, exactly. Yeah. All those strong covalent bonds are really keeping that in a very rigid structure.
Right.
Now, all of the electrons in that lattice model are completely bound up in bonds. Okay?
Right.
So if I want to try and move those electrons around, it's incredibly difficult because they're just so... It's a fantastic electrical insulator. So when Mark, as the real diamond scientist at Warwick, said to me, Julie, I want you to start using diamond as an electrochemist. I said, but it doesn't conduct electricity, Mark, so how on earth can I use this? But I didn't realise that you can start to put impurities into the diamond lattice, and that will start to change its electronic properties.
Okay, well, I think we're going to come on to that in a minute.
Yeah.
But just diamond on its own, that structure, it's not the only thing that has that structure, right? Doesn't ice also have a tetrahedral structure?
It does, but its bonding in ice is very different. It is got a tetrahedral arrangement, but the nature of the bonds are very different. And this structure has very strong covalent bonds which have a high frequency of vibration. And actually one of the amazing properties of diamond, which people don't often know about, is these vibrating atoms can transfer heat extremely well. Okay, so you hardly get any scattering or loss. So it's actually the best thermal conductor of any material known.
Really?
Oh. So does that mean when you touch it, if you had a big enough diamond, it would feel very, very cold to the touch?
Yes.
Okay. And so when you say it's the best thermal conductor, so doesn't conduct electricity, does conduct heat extremely well.
Exactly.
Does that, okay, apart from touching it to your lip, are there other things that you can do to demonstrate this?
Okay, yeah. So what we've got is some ice cubes, and I am going to put in front of Hannah a £1 coin.
Yep.
And I've got a piece of synthetic diamond of a similar size. Ooh. Okay.
I'll be honest with you, the jewellers ones were much
Were they?
Yeah. We really have entered the science part of it.
He's probably had them cut and polished to look really sparkly.
That just looks like a dull disc.
Yeah.
I mean, this is when you believe that it's got carbon in it, right? Because it's like, it's kind of, it almost looks like something that's come out of the fire.
Well, it has come out of the fire. It's come out of a plasma reactor where the diamond is being grown and deposited atom by atom, layer by layer. And you can see there's lots of little sparkles, and they're the little crystals of diamond that are all joined together to make this polycrystalline network.
But the thing that I'm holding now is diamond.
Yeah, absolutely.
Chemically diamond. Go on then, show us what we're doing.
So we've got an ice cube in front of us. Mm-hmm. I think what I will get you to do is take the £1 coin and just press into that ice cube and just see if you can make a dent in it at all. Is it going in? It is a little bit.
A really nice dent.
Okay,
and that's because the heat from my
hand is going through that. What we want to try and show is what happens when you do the diamond. It should, because it's much better thermal conductor, be a much easier process. Does it feel? Yeah.
Whoa!
So it just feels like we talk about a knife slicing through butter.
That Oh,
it's just
really?
It's quite a beautiful feeling, isn't it? It's one of these things. If you're stressed in the evening, just get a bit of diamond and push it against an ice cube and keep doing it.
Wow, I feel like I've got a superpower.
Yeah,
Just cut straight through it.
Honestly, you need to have a go.
Okay,
Yeah,
and now we'll take the dagger-like
Now the
diamond.
this is like a 2 inches long hooked dagger.
Yes.
It feels like it's a long way for that heat to travel as well.
Okay, so press that into the ice. So the heat's going to transmit from you. You are a massive heat source.
Thank you.
Just press in.
Oh my God! Yeah. Oh wow! And it immediately gets freezing cold as well.
The best thermal conductor of any material.
What comes through?
demonstrated.
What about copper?
That's 5 times better than copper in terms of thermal conductivity, but because the heat capacity is lower, it's 25 times better as a thermal diffusivity. So the speed the heat is travelling through the material, 25 times better. So in future technologies, so one of the problems with electronics, AI and all the computing is heat. You've got to be able to get heat out of your high-end chips. The diamond is the solution because it can get the heat out really quickly.
Really fast, yeah.
So there's research going on in the UK and elsewhere where the semiconductor, the active device, be it silicon or gallium nitride, is grown on the diamond or connected to the diamond so the diamond can keep it cool.
Okay, if I wanted to have my own diamond dagger, how do you do this?
You need to start with the source of carbon. So natural gas, methane, has lots of carbon, 1 carbon, 4 hydrogens. So basically you've got to strip the hydrogens off, and you do that by putting it in a plasma. So you heat it up, so about 4,000 degrees C, so the hydrogen atoms fall off the methane. You actually add some more hydrogen to the process, so the carbon atoms rain down onto your substrate, your surface. The hydrogen keeps the surface stable, and atom by atom, you can add layer by layer and grow the diamond.
So you make it from gas?
From gas, from methane.
You make the hardest substance in nature from gas?
You can do it from anything that contains carbon. Whiskey. You can
make diamond daggers from whiskey.
Yeah, and even with the high pressure, high temperature process, where you mimic what goes on deep in the earth, you can make diamond from peanut butter. So anything with carbon in, if you get the conditions right for the bonding to take on this tetrahedral structure.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
Can you tell the difference though? If you had one of these, I mean, this looks very different from the diamonds that we had earlier. But if you did decide to try and grow a lab diamond in the form of the sort of jewellery, emerald cut, whatever it is, could you tell the difference?
Yes, one of the best ways of telling the difference is looking at the luminescence from the diamond. So luminescence means that if I shine light onto the diamond, some of that energy is absorbed, and it's absorbed by the defects in the diamond, moves electrons around from low-lying states to high-lying states, and as those electrons fall back at these defects, they emit light. And the light they emit is specific to the type of defects that are in the diamond. So we can make diamonds glow pink and blue and yellow and any colour you like. But it's the combination of defects in the diamonds that enable us to identify how it was grown, what impurities were there when it was grown, whether it sat in the earth for billions of years. There's a famous professor at Bristol who said, diamonds are like people. It's the defects that make them interesting.
Oh,
and I like that so much.
Because those defects are like the story of its geological history of the earth.
Exactly.
Oh, no.
We're winning you over, Hannah. We're winning you over.
Losing you.
So Hannah, I can there is what you just described. So that's a diamond grown in the lab, cut and polished. It's half a carat, that one, roughly.
Half a carat. So that's my bad.
I've got my mobile phone, and I'm just going to switch the light on my mobile phone and just leave it laying over the top of the diamond for a while. So that's pumping energy into the diamond, some of which is absorbed by the defects that are in the diamond.
What?
Yeah. So now if you take it away, and you just cup your hand, because it's bright in here.
What colour has it gone, Hannah?
It's shining. Yeah. It's actually shining out. Oh no, I hate being wrong about things. Wow, that's extraordinary.
Yeah, it is amazing,
so,
isn't it?
wait, what's the defect in that that's doing it?
So that diamond is grown by high pressure, high temperature. So one of the solvents that's used for the carbon is nickel. And there are nickel complexes with nitrogen in there.
So what is the ratio? I mean, how many imperfections do you need in it to totally change or add new behaviour?
Why didn't you have a guess?
1 in 100, do you need...
1 in a million is a lot for what we do.
Right.
And the diamonds that are produced in the UK, as in it's a real speciality, can produce them with 1 in 1,000 million.
Wow.
And that's all you need.
And that's all you need to change the properties and the behaviour of
exactly.
it.
Yep. It's phenomenal. It's amazing matrix for this host.
Yeah.
So for my applications as an electrochemist, I need to get this thing passing electrons through it. So we go back to this impurities going into the lattice, and I'm going to put an impurity in that isn't this nitrogen that Mark's talked about. I'm going to go for boron. And I need a little bit more boron than Mark needs for his defects, so I'm going to go for 1 in 1,000. So if I can replace 1 in 1,000, I go from being a complete insulator to a good conductor, which is phenomenal. And the other thing that happens is my diamond changes colour. So as I put more boron in, it goes from kind of transparent to blue. So if I look at a beautiful blue diamond, it's actually a semiconductor. As it goes black, I've got a conductor.
Is that what you've got on your necklace?
I've got a blue semiconductor in my necklace, actually. So I had this because it was a semiconductor. This here is some black diamond. So this is actually part of a wafer. We can grow much bigger wafers. So it's a slab of black diamond. That whole thing is black diamond. We've cut bits out of it. And this now, if I wire it up to a battery, I can conduct electricity through that.
Wow. And it still has the same thermal conductivity?
Thermal conductivity, great. It's still ultra strong. As an electrode material, I can now apply, because this is an extremely strong material, potentials, voltages to that, where other electrode materials would simply fall apart.
What does that let you do, though?
Okay, so one of the big things we're really interested in is cleaning up dirty water, cleaning up wastewater. And one of the big emerging pollutants at the moment is something called polyfluoroalkyl substances. I don't know if PFAS, if you've come across this. These are molecules that have a carbon-fluorine bond in them. So you probably would think of Teflon. They're in firefighting foams. The problem with them is that it's incredibly difficult to break them down. They persist. So if they get into our water sources, if they get into our body, they're kind of toxins. And the question is, how do you break them down? And one of the ways to break them down is to try and oxidise them. You need to apply very high potentials to an electrode if it's going to break these molecules down. Diamond is one of the few that can sustain that potential you need to apply. So now there's a massive big technology on trying to use these things to clean up our water sources of pollutants, basically. So,
didn't you say though that you can use any carbon source to grow more diamonds? So could you get like a sort of perpetual cycle going on?
Yep, sustainability. Yeah, you can like whatever you're producing, bring it back
and
try and use
diamonds.
that and make more diamonds. So that's the clever way to do it. Yeah.
Okay, all right. I'm not going to lie, you guys. You are slightly winning me round, but there is a reason why I have long preferred other stones to diamonds, and in particular, I really like white zircon. Okay, and it's a science reason why I really like it, because the thing about zircon is that it is incredibly stable, the structure of it over time, but also it only ever formed at the beginning of the Earth, right? So when the Earth was like this kind of blob of junk and then forming together under gravitational pull, that is when all of the zircon that you find in the ground was created. And in that process, the way that the structure works is that there's no way that lead can get trapped inside, right, inside the crystal structure. However, uranium can. I don't know why I'm telling these two scientists.
Yeah, really should represent
me. Sorry. But I'm just looking for when I make mistakes. So you can correct me.
So far, so good.
So far, so good. Okay, but it ends up being like a cage which can trap like single atoms of uranium inside. Now, the thing about uranium is that over time, over millions and millions of years, it decays radioactively into lead. So if you dig down into the earth and you find a little bit of white zircon, and then you look inside it, and inside of the crystal structure you find molecules of lead, you know for a fact they didn't get there when it was formed. They got there because it was once uranium and then it decayed. And that, my friend, is how they know how old the Earth is. I mean, that's beautiful, no?
That is lovely. That is absolutely lovely. But I can top that. Yeah, have you heard of super deep diamonds?
No.
Yeah, super deep diamonds can give zircon a run for his money. Listen to this.
My name's Professor Graham Pearson at the University of Alberta, and my research topic and passion is super deep diamonds. Normal diamonds form somewhere between about 150 and 200 kilometres deep in the earth. These super deep diamonds form considerably deeper than that, between around 300 and, as far as we know, about 700 kilometres depth in the earth. I mean, these are the deepest bits of planet Earth that anybody is ever going to touch and put their hands on. So they're totally unique archives that tell us information about the deep Earth that is just unavailable in any other way. Any material sat at 700 kilometres in the interior Earth is under tremendous pressure, and it exists in a different crystalline form to the crystalline form that you would find at the surface. So we can make these things in the lab. When we first started to discover these super deep diamonds, the mind-blowing thing is that they contain minerals that nobody had ever seen before in nature other than having cooked them up in the lab. The beauty of these diamonds is that you were able for the first time to stare at one of these minerals that had only ever been synthesized before as a real piece of nature that was pristine, trapped the way it was when it was formed at huge pressures within inside the earth. What we know now is that diamonds are perfectly capable of giving us that insight into all that earth history in just the same way that zircon can, and in fact in more valuable ways, because diamonds are able to probe way more of the earth than zircons are. Zircons are just sampling the little skin, or I'm a mantle geologist, so I call the crust the scum of the earth. So everything comes from the deep interior of the earth, and diamonds tell you that story.
Scum of the earth.
I mean, that is editorialising slightly about where we exist and live our entire lives. But yeah, I mean, you know, he's coming from a all he cares about is the really, really deep stuff. Really, what's going on here? Pointless. But diamonds can do that.
Yeah.
And even the fact that it is the deepest parts of planet Earth that you can touch. Because anything else brought up from those kind of depths just falls apart, doesn't it? Because under the lack of pressure, it doesn't hold its structure.
And Dara, if I may, it's even better than that, because you want a bottle to bring this material up from these great depths to the surface, or close to the surface, where we can get it and see it.
You want a bottle? I mean, what could you make that bottle out of?
Exactly. And you want that bottle to be the hardest, the most impenetrable, the highest atom density material you can, to know that your sample you're studying inside is pristine. That bottle has to be made out of diamond.
Fine, you win. You win, everyone.
So you can see diamonds are cool.
I take it all back. I'm sorry.
They're just a fantastic platform. Make the odd imperfection in a million, and you get a totally different substance.
You never get bored working with diamonds. Every day there's something new and that's being discovered or thought about. It's the most, in my entire career, it's the most interesting material I've ever worked with.
And the best is yet to come, because in the last few years we've made great advances in how we can make it and control the properties, tailor the surfaces. So you're going to see diamond-based technologies coming in the future that are amazing.
Tell you what, though. Put that 15 carat greyed up one on a ring. I would wear that to death.
We'll get one done for you,
Thank
Hannah.
you. Thank you very much.
Thank you to all of our guests, Charlie Bexfield, Julia McPherson and Mark Newton.
I don't like being wrong.
But you're a big enough person that you can admit.
I have the intellectual humility to admit that diamonds are really, really, really cool.
Yeah, but I don't think we're expecting it to be quite as impressive as that.
I do maintain that I would rather walk, apart from the fact that it's so valuable, I would rather walk away with the diamond dagger than the diamond.
Yeah.
That was worth
the diamond dagger is pretty impressive.
I still think they're overpriced.
Yeah, I think if you're showing off to people, going, look at the stone, is one thing, but watch me chop ice live in front of you.
I think it depends on the kind of people you hang out with, but I know which ones my people would be more impressed by.
I just like the fact that we built a whole episode about a thing you don't like. That's nice.
And then they brought in loads of it to play with.
Yeah.
Should we say I don't like other things?
Yeah, do, absolutely. And then people will come in. People just bring them to us. Like,
I hate ice cream.
Yeah, I hate holidays in really, really fancy hotels. Let's disprove that.
Hello, Curios. I haven't used that word for a while. You may have noticed in the last series we didn't get the opportunity to do any curious correspondence. But I have to tell you, by popular demand, you have been sending in your letters, your poems, all sorts of stuff. You sent it into curiouscases@bbc.co.uk. And I think it's only fair that we share some of them, not least with the listeners, but also with you, Dara, because
I've not been around for the correspondence thing at all.
You've not done the correspondence.
No.
It's very sweet.
Okay.
I mean, what I will say is this, buckle up, because they are a creative bunch. So you remember the episode that we did on synesthesia?
I do.
The taste of words. So there was quite a response from that. So there was this message from Emma Miller. Within the first 6 minutes of listening to Curious Cases yesterday, at the grand old age of 51, I learned that I am a synesthete. Until I heard 11-year-old Esther describe how she visualises the week, I assumed everyone in the world sees things this way. How you got to 51? After investigation, I realised I've always had sequence space synesthesia. I visualise the yearly calendar all around me as if it were 3 dimensions. I am genuinely blown away, sincerely thought this was how everybody else sees things.
I'm so proud of Emma, not least because she's realised it's about herself, but that she walks around imagining a 3D calendar all the time and just presume we're all as cool. We're not. And she's there, like in Minority Report, moving dates around with her hands and swooping and filling things in, and she sees it as this living multidimensional grid, and that's phenomenal.
It's phenomenal.
We don't live in that world.
No, I do not live in that world.
I've scraps of paper with and post-it notes.
I mean, barely. Barely. I mostly just wait for people to tell me where I'm supposed to be.
Yeah. Somebody
or complain when I'm not where I'm supposed to be.
Yeah.
More likely. We also got a poem. Don't like to brag. It is here it is. Should we take it in turns? Read a little stanza each.
All right.
Okay. All right. There's something I've spotted in the media, a condition known as synesthesia,
where a person's senses are connected and work in concert when affected.
When feeling happy spawns a hue, like meeting a friend and seeing blue.
When she sees me, she gets a sensation. There's me. I'm just a pigment of her imagination.
Cute.
That is cute.
I strongly suspect they used AI to write that.
No. Phil is a real person. Pigment of her imagination.
Pigment of imagination. That is good.
Yeah, I wouldn't have come up with that.
You know what? You're absolutely right.
Yeah.
Well, thank you very much, everybody. If we get more of these, maybe we'll reprise Curie of the Week.
Yeah, honestly, I'm very impressed.
We used to have badges and everything.
I mean, when I just did Mock the Week, we just got abuse from people. It's a very different
there's
audience.
that too. We just don't read that one out.
Okay, fine, good.
Thanks, Curios.
Thank you.
Hello, Russell Kane here. I used to love British history, be proud of it. Henry VIII, Queen Victoria, massive fan of stand-up comedians, obviously, Bill Hicks, Richard Pryor. That has become much more challenging, for I am the host of BBC Radio 4's Evil Genius, the show where we take heroes and villains from history and try to work out were they evil or genius. Do not catch up on BBC Sounds by searching Evil Genius if you don't want to see your heroes destroyed. But if, like me, you quite enjoy it, have a little search. Listen to Evil Genius with me, Russell Kane. Go to BBC Sounds and have your world destroyed.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
This BBC podcast is supported by ads outside the UK.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
BBC Sounds. Music, radio, podcasts.
You're about to listen to a brand new episode of Curious Cases. Shows are going to be released weekly, wherever you get your podcasts. But if you're in the UK, you can listen to the latest episodes first on BBC Sounds. I'm Hannah Fry.
And I'm Dara O'Brien.
And this is Curious Cases.
The show where we take your quirkiest questions,
your crunchiest conundrums,
and then we solve them.
With the power of science.
I mean, do we always solve them?
I mean, the hit rate's pretty low.
But it is with science.
It is with science. We're going to do an episode on love today. Now, I'm a bit cautious about talking about this topic because one of the first things that I ever did for like a public audience was a TED Talk called The Maths of Love. This is when I was young, fresh-faced, newly engaged, and I stood up confidently on stage and proclaimed how easy it was for you to use equations and mathematics to describe romance and success in long-term relationships. Would you like to know what's happened since then?
Yeah, go on.
Getting divorced. Okay, let's...
What's the matter of that?
True love doesn't always last, put it that way.
Okay, well, we're not claiming we'll solve it, all right?
No, we are not. Yeah. Should we have a listen to the question?
Please.
My name is Alison. I'm from North Hertfordshire. And my question is, what happens to our brains when we fall in love? Why are teenagers prone to have crushes? I also remember from when I was young, it's a long time ago, how uncontrollable love is. I had a big crush on the Beatles, George Harrison, and I really don't know where that came from. I'm trying to describe it. What did he look like? Quite pinched and hungry looking, and it's that sort of rawness that was appealing.
She's got a type.
She certainly does, and still has, by the sounds of it. Good woman herself. Look, I find it very interesting because young men, we don't do the pop star crusher thing in quite the same way, or certainly it's not industrialised in the same way as it is for young women.
No, I agree, but then I've always had a bit of a theory about that because I think that it's a little bit easier for young boys to lust after women. Right, it's sort of more socially acceptable. I think like you kind of have to be a bit more cloak and dagger about it as a young woman. And I sort of think that the pop star thing is like a very socially acceptable way for young girls to explore their sexuality.
Okay, grand. I also do remember there being a specific phase where, looking back, I was clearly training in how to, because I would fancy someone's a term you'd have a crush. You'd crush on somebody for like a discrete 3 to 6 months, and then bang, stop. And so you'd stare moon-faced across the classroom at some girl when you were like 12, 13, and then bump, that's over. Now you're staring this direction at somebody else. But clearly there's some process being trained in the body or the head, the chemicals being released, whatever, that then became your basis then for building relationships later.
Yeah,
so there's something happening,
and there absolutely is. I mean, not sort of silly equations and so on, but genuine, actual science that we can properly talk about.
Good, but we promise we're not going to pin love like onto a board like a butterfly and destroy it.
Frankly, I don't think I really did that either. But I was just way too overconfident.
Okay, fine. So, joining us to explore the chemistry of love, we have Dr. Dean Burnett, neuroscientist and author of The Idiot Brain and the Happy Brain.
And Dr. Anna Mayton, an evolutionary anthropologist and author of Why We Love. I mean, Anna, you literally wrote the book on the subject.
Hopefully so.
So, okay, we heard from Alison and her mad crush on George Harrison from the Beatles. Did you have any teenage crushes?
Yes, I did. The big one was River Phoenix.
Right.
Which is really showing my age. But I remember him dying outside the nightclub in LA and just being devastated for weeks and weeks and weeks. And I can still remember the moment when it happened, when I heard it.
Actually, for weeks?
I was absolutely bereft.
Okay, so, I mean, why?
Why River Phoenix?
I don't mean specifically why River Phoenix, but like, how on earth can this possibly be advantageous for humans to develop these sort of almost fictional relationships in our minds and then react to them with the same emotions that we might do a real relationship?
It's really training for being an adult. So the majority of our crushes, which we actually now call parasocial relationships, they happen when you're a teenager. And that's because it's allowing you to explore relationships and how love feels and your sexuality and all those different things in a safe environment. So you're unlikely to get properly hurt by being in that relationship. So yeah, it's allowing you to.
You were hurt.
I was hurt. But it's allowing you to explore those emotions and finding out, who you fancy, who you don't fancy, what kind of person attracts you, that kind of thing.
Okay, but then is there something about the types of people that people crush on? I mean, Harry Styles, for example. I 100% get it, but there are some like particularly crushable people.
There are.
Maybe a bad choice of words.
Yes. Yes, there are. And it's because, we're still going to look for really attractive people. Most famous people are above average attractive in one way or the other. And our brains don't understand.
She's saying that to us, Darren.
Yeah, obviously.
I took the compliments, but
I looked at him directly when I said that. Yeah. And our brains don't understand screens. If you think sort of photographs, films, telly are actually a very, very recent thing in evolutionary time. So our brains don't discern that screen. They think that person is standing in front of them, obviously usually highly attractive, highly successful, ticks all those lovely boxes for going forward and having a relationship with this high value person. So we're going to fall in love with famous people because they carry all this really good indicators of being a very valuable mate, basically.
But then at the same time, that interaction is entirely one way. And it's like, do we not notice that we're not getting, they're not really getting anything from us?
We do, but what's really interesting, what's amazing about the human brain and what's amazing about parasocial relationships, which also goes into religious love actually, is the ability of humans to actually form complete relationships in our minds. So without ever actually interacting with that person in person in front of you, without that person manifesting in physical form, we are capable of having a full relationship. And actually with crushes and parasocial relationships, we know teenagers form proper psychological attachments to these people. They provide that secure base from where that teenager will go out and explore the world. And particularly for sort of LGBTQ plus kids, they're really important attachment figures.
As you're talking, do we have parasocial relationships only for teenage crushes, or do you get them throughout the rest of your life?
You get them throughout the rest of your life. So a parasocial relationship can be with an actor, with an actress, but it can be with a character in a book. So you might have a parasocial, crush on somebody in a book, and they are throughout your life. Now, what we used to think was if you had them as an adult, that was sort of a psychopathology. There's something a bit odd with you. But recent research has shown actually no, people who have them throughout their life, it's not like they're making up for a lacking in their social network. Usually they're very happy, they're very psychologically strong, they've got a family, but this person is fulfilling something to them in their social network. So a lot of people have parasocial relationships throughout their life.
And does it specifically have to be crushes, or can it be, I have lots of girl crushes, for instance. So it could be like just an admiration thing rather than necessarily sexual.
Absolutely. Love is a massive spectrum. And while we talk a lot about romantic love, actually, you can love these people in lots of different ways. So it could be just a girl crush or someone who you really, really think if you met, you would be best friends, So yeah, it could be anybody that you admire.
Is there any particular reason we always associate this kind of the parasocial crushes with girls as opposed to boys?
Do you know what? I just think girls talk about them more. Girls are more likely to sort of be online fans, so you're a Harry Styles fan or you're, a Lady Gaga fan or whatever. You're more likely to join a group and be really loud about it and make lots of fuss about it. Yeah.
And I don't want to, look, these are very broad generalisations, obviously. I'll throw another broad generalisation. We fixate on a football team. Is that, and that is by some distance the most long-lasting and dedicated relationship in our lives, like whatever. And there is a definite point where we pick a team and that's it. That's and our mood is linked to their successes or not successes. Does that fall into this in some ways? Some sort of, I certainly, there's dopamine rushes, like all the chemicals we have.
You're more flustered talking about this than you were about your crushes.
Stop it, listen, I have given, it defines my life. I'm just always intrigued with the fact that this is literally, you hit the point and you stop and you love this team and you love them forever.
Absolutely. But humans want to be the members of groups.
Yeah.
That's what we love to be part of. And so you found your group, you found your identity, you've all congregated around this totem, which is the football team. And that's where you're going to stick. It's a sense of belonging. And all the behaviours that football teams do, and when you go and watch your team and you all chant and everything, you are in a love relationship with that team and also with the crowd that are around you.
Very much so. Very much so.
Dean, how about you? Any crushes to report, football or otherwise?
No, I was what we call a late starter when it comes to the romantic field. I've had 2 girlfriends in my life and spent 20 years married to the second one. So, like, I was in school, I was very much this girl hasn't like pepper sprayed me yet. I mean, she must like me.
It's a low bar.
Yeah, and my one previous girlfriend is currently on her second wife, so she's better at women than I am. So technically, she should be here. Me being here talking to people about love is like the 55-year-old guy in the crowd, like yelling instructions at the Premier League footballers. So, like, yeah, I know the theory, but you put me on there, I'll be stretched off in seconds. I can't help you there.
Sure. Okay, so Alison was talking about how powerful, uncontrollable these passions can be, how real they can feel. In terms of the drive for this, though, okay, not to be too much of a love skeptic, and I promise I'm less skeptical than this question makes me appear. But is love actually necessary? I mean, from a sort of evolutionary perspective, really, you just want to pass on your genes. You just want, to be able to successfully mate, right, reproduce. Why does love matter as part of that?
It all feeds into survival as well, because you form part of a dynamic, you form part of a team, and if there's 2 of you, if you are the sort of species which does care for your young rather than strength in numbers, like fish and reptiles, like loads of eggs, okay, good luck, and just wander off. That's they have a very different attitude to parenting, and obviously they don't love their kids like a mammal would. But if there's 2 of you, then that doubles the chances of protecting, providing, and when you're part of that dynamic, it becomes your odds of survival increase in certain species. So yeah, it can be very necessary, very helpful.
And what is chemically happening within the brain?
Yeah, lots of different stuff. Especially when you first fall in love, there's a lot of neurochemical changes going on. Obviously, dopamine, the pleasure chemical, as they say, that goes up centrally. But it's not just about experiencing reward. It's all about motivation to find the reward and anticipation of the reward. So you become like, I love this person. They are my favourite thing. I want to see them. I expect to see them. I will do whatever I can to see them. Noradrenaline increases, which is involved with focus and attention and short-term memory, so you're thinking about them all the time. Also disrupts sleep, so obviously you're losing sleep over the object of your affection. And I think one of the particularly interesting ones is serotonin goes down, and that's normally associated with the opposite, being not depressed and stuff. But people are love sick. They do become really sort of preoccupied and shaky, and they seem unhappy a lot of the time if they can't be with the object of their affection particularly. And all the different hormones and neurochemicals interact to make this weird situation. And it also does stuff like lower the activity in the amygdala and the sort of fear and threat detection mechanisms, because people in love, they can also be quite happy, euphoric, because their ability to detect threats has dropped, and the brain doesn't do that so well anymore, which is why love is blind. People can end up with the same person 2 months solid, and all their friends are going, why do you like this one? They're awful. They've got all these bad habits, all these bad traits. You don't see it. You don't see it because your brain's not in that mode.
Rose-tinted glasses.
Very, very thick rose-tinted glasses. Rose goggles even. Rose Weldon goggles.
Rose Weldon goggles.
So we've dipped our toes into the flood of brain activity that turn us into fools when we fall in love, but a lot of our initial understanding of this stuff has a surprising origin, studying rodents, especially voles.
I am Carmine Periante. I'm a professor of biological psychiatry at King's College London. With romantic love, if you like, and especially exclusive relationships, a lot of the research comes from voles. The voles are small rodents. They are really small. They're around 40 to 60 grams each. And the prairie voles are in the prairies, so usually in grasslands in North and Central America. And the mountain vole are more mountainous regions. Now, what is interesting about these 2 species is that although they look really similar, their behavior in terms of love and relationship is completely different. The prairie voles, they do form long-term relationship with a partner. They look after the children of their offspring together, and they have a preferred partner to which they remain regularly present with. The mountain voles are completely unfaithful, and they're unable to form long-term relationship with the same partner or to look after their offspring with their partner. And by looking at the brain of these animals that are so similar yet so different, we can understand or start to understand the basis of love. The prairie voles have much higher level of what we call receptor for oxytocin. So oxytocin works by binding to a protein that then alert the brain that oxytocin is working. It's almost like a key and lock mechanisms. Now, the prayer balls have many more locks available, so that when the oxytocin is produced in the brain, everywhere in the brain is activated because there's so many locks there. However, the mountain balls, the unfaithful one, doesn't have so many of these locks, and so the oxytocin cannot really have the same widespread effect on the brain, and that's probably why they don't form relationships.
So, in summation, prairie vole's good, mountain vole's bad. If you're picking a partner, yeah, it's got, yeah, that's a little harsh. But
there's the Catholic coming out.
Yeah, oxytocin. So, what would we describe the prairie voles as? Is this too human a term? Monogamous, biologically monogamous?
The problem with the word monogamy is that actually there's no truly monogamous species. True monogamy doesn't exist, and even though we talk about monogamous species like swans are monogamous or gibbons are monogamous, actually when you observe them they will all go off and have a sneaky mating, because from an evolutionary point of view it would be very silly to restrict yourself. So they tend to be what we call socially monogamous, so they will stick together for a lesser or greater period of time to raise offspring, to make sure those offspring are raised to survival.
And the mechanism that does this is oxytocin.
In voles, it's oxytocin. Voles were really helpful initially because we had no idea what the neurochemistry of love was at all. And they really did open that up for us in terms of understanding. They were the perfect model, having a polygamous one and a monogamous one to show us what the differences were. They're not great proxies for the human brain because the human brain is very, very complicated and we have very, very different, very long-term relationships in lots of different contexts. So whilst we can start with oxytocin, and oxytocin's certainly there in the human brain, it really is more of a background chemical for us. And it's
I mean, people try to sell oxytocin spray. Mm-hmm. Would that work?
There used to be something you could buy from eBay. I don't think you can anymore. But they claimed that if you squirted it up your nose, they called it a pheromone, which is wrong anyway. But if you squirted it up your nose, people would flock towards you.
Oh, you wouldn't fall in love with other people?
No, they would. I mean, it's all wrong, but I think they did quite well.
Hang on, if you squirted up your nose?
If you squirted up your nose, actually, we use it in the lab. If we squirt it up people's noses, it makes them more open to forming social relationships, which is what it does. It's not a pheromone, but they sold it as a pheromone.
Because nothing woman likes more than a man who's coughing and spluttering and pawing at his own nose. It's a very attractive thing. That feeds my mate value enormously.
Yes.
Yeah. Amidst all the chemicals swirling around in your head, is there an addictive element to this?
There absolutely is. So we've talked about sort of oxytocin, dopamine, serotonin, and those are all really important chemicals, mainly at the start of a relationship. They underpin the attraction stage of love. But we need something that actually underpins our relationships for decades, whether we're talking about romantic love or child-parent love or whatever it might be. And those chemicals, unfortunately, aren't powerful enough to do that. We become tolerant to them. They don't last that long. So actually, what underpins primate long-term relationships is beta-endorphin. And beta-endorphin is an opiate. It evolved to be your body's painkiller. And over time, we think via social rejection, it's been co-opted into the social sphere. And it's actually what's released when primates interact with each other in long-term relationships. And the wonderful thing about beta-endorphin is it is addictive like any opiate. It's like morphine, it's like heroin. So it's a very simple mechanism. You're with the person, you do an interaction that releases beta-endorphin, touch, laughter, whatever it might be. You get that wonderful opiate euphoric high, you go away from them, you go a little bit of cold turkey, and you will return to them to satiate that physiological and psychological withdrawal. And the other good thing about beta-endorphin is oxytocin and things like that are only really released mainly in a powerful sense in what we call the reproductive relationship, so between parent-child, between lovers. So you need something else, and beta-endorphin is released by lots and lots of activities that aren't linked to reproduction. So dancing, singing, exercise, touch, laughing, having really good conversations, having a hot curry, all of these things release beta-endorphin.
It's like filling up your well.
Yeah.
Yeah.
So
Nice.
beta-endorphin would also explain why you love your hobbies or pastimes as well, because they would
Absolutely.
Are we going back to football?
We are.
I'm not. I am not. I feel I've satiated myself there.
Is football the most important romantic relationship?
Well, you know, I don't want to say this publicly, but how do you experiment on this? I mean, do you? Look, how I would do it is I would simply invite in the students and go, I'm going to wire you up, and then you're going to fall in love with me, and I'm going to measure what happens there.
Okay, yeah.
Would I
wouldn't
get
get past
funding?
ethics,
No, okay, fine, fair enough. Can you take a blood sample and see these chemicals? Are they,
It depends on the neurochemical. Oxytocin, absolutely. You can get oxytocin in lots of different ways. Wee, saliva, blood, whatever you want. The other ones involved in love, unfortunately, don't cross the blood-brain barrier. So we can't take a blood test. Serotonin, dopamine, beta-endorphin don't. So we have to do various forms of scans. The ones to really, really show that we know a neurochemical's been released and we know it's had uptake by the receptors is a PET scan, which is radioactive. So you don't get a lot of people volunteering for those unless they really, really want the money. The other way you can do it, you can use a proxy. So my students who don't have quite as much money, they use proxies. And what that means is because we know beta-endorphin is a painkiller, what they will do is they will test somebody's pain threshold before they've done whatever social interaction it happens to be. And the ways we do that, sounds awful, but we might put a blood pressure cuff on your arm and inflate it until it reaches pain tolerance. And then you say, ow, that really hurts, and we stop. Or we might get you to plunge your hand into ice cold water and see how long you can do it for. Or over a hot plate, which we don't do that often because that can go wrong. But that's what you do. Then you get them to do whatever social interaction it might be. And then you test the pain threshold again. And the pain threshold will have gone up because beta-endorphin has been released.
Oh, but my experiment where, why don't you just fall in love with me? That's unethical. But
That's great.
Hand over a hot plate, not a problem.
Not a problem. We have
So if I did that initially, the cold water, taking my hand out of freezing water, then spent time with somebody I loved, and then did it again, I should feel...
You should last longer.
Right,
because
okay.
your pain tolerance has gone up. And generally we do find that. So what we tend to do with these studies is you will start with something like that because PET scanning is very expensive. You'll start and think, okay, I have possible proof of concept here that this is what's going on. We will now put lots of people in a PET scanner and prove it.
I'm sorry, so we spoke earlier about the drugs that swirl to your brain when you're falling in love and you're all happy and the dopamine and all that. Is there an unhappy one? Is there an analog for when you get dumped and you feel terrible? Is there a bad drug?
No, what you're doing is you're going cold turkey. So there's two things that happen when you're dumped. You have a physiological withdrawal and you have a psychological withdrawal. So the physiological withdrawal is the withdrawal from the neurochemistry, and particularly if you're in a long-term relationship, that's a withdrawal from an opiate. And so if you imagine a heroin addict withdrawing, so suddenly you've gone from quite a high level of beta-endorphin, happy, euphoric, all your little painful niggles have, been covered up, and you suddenly go down to nothing. You go cold turkey. So that's why physiologically it's actually incredibly painful. It can be physically painful to be dumped. And that's why it can be so hard to get over. But actually some people are genetically predisposed to feel worse when they're dumped than other people, unfortunately. There is a gene that causes people who are dumped to feel much worse. It's known as a gain-of-function gene, and we think these people probably exist at a higher level of beta-endorphin than everybody else. They maybe have more beta-endorphin receptors because that's what it's associated with. And so when they're dumped, their cold turkey is much, much more horrible than it is for us. About 2% of the population carry it. So when we find one, we get very excited. But you can actually, when you talk to people, you can see it coming through in their experiences of being dumped. It's actually quite a powerful gene to hold.
Wow. Okay. I mean, you're very excited, but I mean, in the experiment where they have to fall in love with you, I then have to break up with them.
Well, they'll be the ones who are dribbling on the floor.
That is okay. You come back in 2 weeks, and you're not going to enjoy that part of it. But
I expect it's not so bad now, is it?
Yeah.
What's that spray you've got under your desk?
It's all very well talking about this as if we're prisoners of our chemistry or our genes, whatever. We have built enormous cultural norms around these, and they differ from culture to culture as well. Am I right?
Oh yeah, totally. I mean, I think in the Western developed world, we all think marriage as being like, you fall in love with someone, you get married, and then you go through all the different parts of life as a married couple. But a good massive chunk of the human race believes in arranged marriages. You get married first and then develop the relationship and go forward from there. That's totally normal for them. So this whole idea of, must fall in love, get married happily ever after is like a cultural creation, but it's not the only way of doing things. So we have all this cultural inertia, this cultural expectation on relationships, on how they should work. And I talked to Dr. Petra Boynton about the relationship escalator, the idea that, of course, you get together with someone, then within 2 years to get married, and then you got children, and then you've got to move to the countryside, and you've got to have all these expectations of stages, and the very concept of where's this relationship going? It's like, where does it have to go? Who said it?
It just is.
It's not a vehicle. It's our thing. And I think there's been a lot of sort of, I wouldn't say harm, but I think it's been unhelpful, the cultural obsession with happily ever after. Because it suggests then...
I'll say, Dean. Good.
Yeah, I think that's the cultural expectations do put a lot of pressure on people when they're in love, and I think like perhaps we do better without sometimes, I think.
And we emphasise different things in different cultures.
We do, yeah. Love is actually the one really big, I won't call it an emotion because it's not an emotion, but the one really big phenomenon which culturally we differ on massively. So if you think about anger, we can all kind of express anger in the same sort of way around the world. Love, the definitions of it vary cross-culturally. So if you look at somewhere like Russia, for example, if you ask people to define love in Russia, they actually define it as suffering and as self-sacrifice. So it's actually quite a negative experience.
More orthodox.
Whereas let's say we go to Senegal. Now in Senegal, love is seen as more of a family-based spiritual experience. So that's what love is there. If we go, we go to Brazil, which is a Catholic country. A lot of it there is again, it's based in the family, but it's all about sort of self-sacrifice and doing good for other people. So love, and then obviously in the West we've got romantic love, which we've spoken about, with the idea that there's the one and that you're going to skip through the days and it's all going to be wonderful and blah 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 blah, and that's what we think love is here. It's meant to be this very positive thing. So you will go around the world and you will get hundreds of different ideas about what love is. Even actually, if I sit in a lecture theatre and say to 300 people, how do you define love, you will get 300 answers, because it's highly subjective and it's highly culturally prescribed.
I really like the way that you describe that, as though it's sort of the difference between romantic love and love more generally actually isn't this hard boundary. And it depends where you go and depends who you talk to, that one can kind of melt into the other and backwards. I really like that idea.
Well, that's what I love about the work I do is I think in the West we have this massive obsession with romantic love, and that's because it's a multi-billion-dollar industry. But actually what's wonderful about being human is you can experience love in myriad different ways, and as you say, it's like a spectrum. They all kind of merge in and out. They have characteristics in common, and then they have bits that are different, and you can have so many different sorts of love. You can love a god, you can love a celebrity, you can love your dog, you can love your friends, you can love your community, you can love
God. Everyone stop loving me. Okay?
You can love your football team, you can love your parents, your children, and that's what's wonderful about love. So actually I think when we talk about love, we need to broaden what we mean. We don't necessarily mean romantic love.
And look, I mean, we've all been in relationships that have been difficult. I know that I strongly committed once, and then they started to lose matches, and it just was really difficult time for us.
Yeah. Maybe you've got that gene.
Yeah. Literally 60,000 of us with that gene every 2 weeks in that stadium, weeping our eyes out. They're going, why must they do this to us? Why? Thank you, by the way, for all taking that seriously. Thank you for not automatically dismissing it. Yeah.
I just quite like the fact that we ended on, what frankly felt more like a therapy session than a science show. But this idea that actually the sort of biological definition of love is much broader than we sometimes give it credit for.
Oh, massively.
Well, thank you very much to our guests, Anna Machin and Dean Bennett. What a great discussion.
I loved it.
Well, I hope that answers Alison's question. Overall, crushes are a way of practising, and no, we don't understand why you like George Harrison either.
I mean, the unanswerable question and the great randomness is, why not John or Paul?
If you're going to be out there, go for Ringo, for goodness sake.
So wow, it's almost we're left knowing less in some ways about the random nature of love. Because George is grand, but it's John, isn't it? It's John.
It's obviously John.
Hello, this is Marion Keyes.
And this is Tara Flynn.
We host a podcast you might like for BBC Radio 4 and BBC Sounds called Now You're Asking.
Each week we take real listeners' questions about life,
love,
lingerie,
cats,
dogs,
dentists,
pockets,
or the lack of.
Anything really.
And apply our worldly wisdom in a way which we hope will help.
But also hopefully entertain. Join us, why don't you?
Search up Now You're Asking
on BBC Sounds.
Thanking you.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.